My name is Costin Pacoste, and I will be talking today about dynamic effects from pedestrians on pedestrian bridges, which is a topic which has gained much importance in recent years. About me, very short, I am a civil engineer and I have a PhD in structural mechanics. I work at a design company called Ely Consult, where I am the chief technical officer. I also work on a 20% basis at KTH. That being said, I am going to now stop the video and start sharing my screen so that we can start the lecture. One more thing, please keep your microphones muted, but if you have questions, unmute them and ask your question. That being said, let's go into the lecture itself. What we are going to talk about is vibration and comfort on pedestrian bridges. And the issues we are going to cover are, first of all, a definition of the problem. And what do we mean by comfort? For example, which are the criteria by which we judge the comfort of the pedestrian crossing the bridge? We will also talk about human-induced vibrations, and in this context, we will talk about loads. What kind of loads do we need to account for, and how are we going to account for these? And then, of course, we will talk more about design procedures. So what do we do as designers faced with the problem of checking the comfort of our pedestrian bridge? There are other issues in the context of dynamics. There are other issues which are important. One of them is vibrations induced by traffic, but we are not going to touch upon this subject, which deserves a couple of lectures in itself. At the end, I am going to give you some examples of pedestrian bridges that we have checked at Ely Consult for dynamical problems. And these are bridges which connect to the new national arena in Stockholm. Now, if we are talking about the definition of the problem, the first question we need to address is what is the level of performance we require from the structure? So what do we look at when we judge the performance of the structure? Then, of course, establishing criteria is not enough. We need to establish which type of loads we will apply on our structure to verify these criteria. And since we are talking about dynamic problems, we will need to look not only at the amplitudes of the load, so at the maximum force that we apply, but we also need to look at the frequency content of the loading. So what type of frequencies are present in our load definition. Then, of course, that will come a bit later. We need to do a modeling of the structure and perform the analysis. I'm going to talk about this on on a practical example. Now, there are two types of, talking about comfort criteria, there are two types of criteria. The first one is expressed in terms of eigenfrequencies, so the eigenfrequencies of the bridge. And with respect to this criterion, Eurocode has two values, two threshold values. One is for vertical vibration modes. If these are higher than 5 Hertz, then we do not need to perform a control of the motion of the bridge. What I can say about this criterion is that since I have started to look at this problem, I rarely, if any time, encountered a pedestrian bridge with frequencies higher than 5 Hertz. This is a very high value for the first fundamental vibration mode in the vertical direction, and it is rarely, very rarely fulfilled. We have also another criterion which refers to the eigenfrequency for horizontal or transversal and torsional vibrations. We say we are much more strict here, and we will see in a short while why. We are stricter here. We require the horizontal and torsional vibrations to be higher than 2.5 Hertz. If these eigenfrequencies conditions are not met, then what we need to do is check the amplitudes of the vibration which are induced by the dynamic loading generated by the pedestrians. So if we do not fulfill the eigenfrequency criterion, then we need to look at the vibration amplitude. These vibrations amplitude and the criteria expressed in terms of vibrations amplitude are for most of the codes given in terms of acceleration. Some codes will give these limits in velocities, but most of them will give the threshold values for the amplitudes, vibration amplitudes in acceleration. There is one problem when it comes to vibrations amplitudes and the criteria related to these. These are very subjective. So essentially, what I would perceive as non-disturbing, a value of the acceleration that I myself will perceive as non-disturbing, perhaps some of you will perceive as very, very disturbing. So there is no clear threshold. It's the threshold values are most of the time defined in terms of probabilities of adverse reactions to the motion of the bridge. So perhaps if we fulfill the criterions in vibration amplitudes, 95% of the people crossing the bridge will say, okay, this is an okay bridge. This subjectivity is also reflected in the way in which various codes define these threshold values for the maximum accelerations, for instance. If you look, and the reason I'm showing you this table is to see that there are no two codes giving the same threshold values. And this is an effect of the fact that the vibrations amplitude criterion is very, very subjective. So each code, based on its empirical data, decided something. Talking about these criteria in vibrations amplitude, there is one problem with most of the codes. First of all, most codes do not differentiate between different bridge locations and functionalities. So they would use the same threshold values, regardless of the fact that perhaps the bridge is somewhere located in a very remote area where perhaps it will be crossed by 10 people a day, so that you will have the threshold, the same threshold values for this type of bridges, remote areas, very few pedestrian, as for the bridges in a densely populated area, say like Stockholm, which will be crossed at certain times of the day or days of the week by a very, very large number of people. This is the case, for instance, for the bridge, the pedestrian bridge linking the subway station and the area where the National Football Arena in Stockholm is placed. They will have, whenever there is a match, you will have a very dense group of pedestrians crossing from the subway to the arena at the same time. This is one drawback. We don't have a differentiation depending on bridge location and functionalities. But there is also another drawback, which is more severe in most codes. The threshold values do not differentiate between vertical and transverse and horizontal directions. And we will see a bit later that we need to separate this kind of effects. So the effects in vertical direction from the effects in transversal direction, in the horizontal direction. One of the reasons for having to separate these effects is related to two effects. One is synchronization and the other one is lock-in. What are these effects? Synchronization would be the tendency to walk at the same pacing rate. So a group of people which manages to synchronize itself and walk at the same pacing rate. That would be the case, for instance, if a group of soldiers are marching over a bridge. The rule of marching in the army will force them to synchronize their pacing rate. But then we have also another phenomenon, which is called the lock-in phenomenon. And lock-in could be defined as the tendency to synchronize the pacing rate with the motion of the bridge. So one is synchronization in itself, tendency to walk at the same pacing rate, regardless of what that pacing rate might be. Another thing is the tendency to synchronize that pacing rate with the motion vibration of the bridge. Now, the lock-in phenomenon is very, very dangerous. And since you have gone through the course on structural dynamics, you will realize immediately why, because the lock-in will generate very high amplitudes on the bridge. It will generate resonance, and with resonance follow very large amplitudes of the bridge motion. The good thing is that the lock-in phenomenon is not an issue for vertical vibrations. And this conclusion is based on tests performed at a bridge in Italy, in a town called Solferino. And the results of that test suggested that a crowd of pedestrians are not really able to maintain the walking at the resonant frequency when the motion of the bridge becomes very strong. And the reason for this is that they will simply lose balance, and they will slow their pace, or they will simply stop walking, and the resonant phenomenon will disappear. So lock-in will not actually be an issue for vertical vibrations. However, lock-in is possible for lateral excitations. And the explanation is very simple. Once the bridge starts to move, in order for the people not to lose their balance, they will adjust their walk to the motion of the bridge. This is what happens on a boat when the boat is rocking from one side to the other. It's the sailor's walk that will essentially try to compensate for the motion of the bridge so that the pedestrian maintains his balance. Of course, if this happens, as for instance at the Millennium Bridge in London or at the Solferino Bridge in Italy, this is a very serious, very critical issue. It can actually lead to structural damages on the bridge. So whereas the vertical vibration are a question of comfort, so serviceability limit states, the lock-in phenomenon generated for lateral excitation, it could be a question of ultimate limit states. It can lead to synchronized motion. It can lead to very high vibration values, resonance, and it can damage your structure. Of course, it's not enough when we are talking about lock-in. It's not enough to have just one person walking in synchronization with the bridge motion. We need to have a critical number of pedestrians that will generate enough emotion large enough so as to be felt by everybody and start being a synchronization signal, if you want. There have been attempts to quantify this number of pedestrians. It will depend on the modal mass. The critical number of pedestrians will depend on the modal mass, on the frequency of the first lateral mode, on damping, and so on and so forth. So one way of dealing with this is to make sure that the critical number of pedestrian is not reached for the particular bridge. Another way of making sure this lock-in phenomenon will not occur is to limit the horizontal vibration at 0.1 meter per square second. You see it at the bottom of the slide. This value will not be related to comfort, but to the risk for lock-in. Now, what's the assumption behind this? Essentially, the condition expressed in terms of critical number of pedestrians or in terms of maximum value of the horizontal acceleration expresses the same thing. You need to reach a certain level of vibration for the people on the bridge to experience this as a signal for synchronization. For me, it's this proposal, which comes from a French research group, etc. This one is better than the number of pedestrians. Now, having said that, CETRA also proposes threshold values for vertical vibrations. And the good thing about their proposal is that it differentiates between various degrees of comfort. So for instance, if the maximum acceleration is less than 0.5 meter per square second, then we will say that this is a high comfort threshold. For mean comfort, we will have values of maximum acceleration between 0.5 and 1 meter per square second. And a low comfort will be with maximum values between 1 and 2.5 meter per square second. What is the low comfort? What is the meaning of this low comfort? This actually means that under certain circumstances, the vibrations of the bridge are very clearly perceptible, but they are not actually intolerable. What is intolerable is values of the maximum acceleration above 2.5 meters per square second. This is considered a bit a panic threshold. So if the vibrations are higher, then people will start panicking. The motion of the bridge is too high. They will not, it's not anymore a question of comfort. It's a question of people fearing that the bridge will collapse and they will panic. So this is absolutely unacceptable. Up to this value of 2.5 meter per square second, we have 3 different thresholds defining 3 different degrees of comfort: high, mean, and low. All these vertical vibration, horizontal vibrations are, as I said, proposals from the group of French researchers, etc. They have now found their way in the Eurocode, and practically most of Europe uses these proposal and these criteria. Now, you see here, these values are not in any way related to the dynamic characteristics of the bridge, of the motion. Say, whatever the frequency of the motion is, if the value of the maximum vertical acceleration is less than 0.5 meter per square second, then vibrations will be considered very low and a high degree of comfort will be achieved, at least according to CETRA. This is not quite the way in which, for instance, the ESO norms will express the threshold values for the accelerations. The ESO norms will give you a base reference curve. You see it here on the slide, which will be dependent on the frequency. So as you see here, the lowest value will be between 4 and 8 hertz. If the frequency of the motion is between these two values, 4 and 8 hertz, then the threshold values for the accelerations will be at their minimum. And this is to mark that people do not respond in the same way for various frequencies of the motion. So we are most sensitive for vibrations in the frequency range 4 to 8 hertz. And this is reflected in the base curve by the fact that the value of the acceleration is at its lowest point. For other frequencies, the threshold values will increase. One other interesting thing about the values given in ESO is that they are not given in terms of maximum acceleration, but they are given in terms of root mean square of the acceleration. The root mean square is defined here in the equation is in the slide, so it's a integral over a period of time equal to tau. So from an integral from t0 to t0 plus tau of the square of the acceleration. And this is then averaged by tau, which is the duration of motion we are considering. Normally, we will take tau as 1 second. This value, of course, for a harmonic motion is very easy to compute, because for a harmonic motion, this is the time function of the acceleration is harmonic, so it's a sine or a cosine, and we can perform this integral explicitly, and we will end up with the root mean square of the acceleration equal to the maximum value divided by square root of 2. So for harmonic loading, this criterion is very easy to apply. However, for a general type of time dependency, the way in which we estimate the RMS value is a bit more intricate. The reason I'm showing you this is just to plant the idea in your minds that although these are very clear-cut threshold values, there is a frequency effect on the human perception. Now, having said that, let's stop for a bit and see if you have any questions. Please, if you have a question, unmute your microphones and simply ask it. Well, I'll take it that there are no questions. So let's continue with the lecture. And let's talk, we've seen the criterion, let's talk about the dynamic loading that is induced by people walking or running on or jumping over a bridge. And what are the things that we need to look at? Well, first of all, the amplitudes of the loading. So which is the maximum force that can be attained. Then we need to look at the time variation, and we also need to look at the frequency content of the loading. And then, of course, we need to define the number of pedestrians that we are going to consider for the design of our bridge. These are the 4 issues that we need to cover when we talk about dynamic loading. Now, the good thing about dynamic loading, at least for walking, is that we have very good empirical data defining the force that is generated under our feet when we walk. What you see here in the slide are 2 diagrams of the force divided by the static weight, A for slow walking, B for fast walking. What you see here is, of course, the fact that at certain points in time, the actual dynamic force which is applied on the bridge is higher than the static weight. And these 2 points are 2 characteristic situations when we walk. The first one is whenever taking a step, the first thing we do is we plant our heel on the ground. We plant our heel and we will exert a force which is, even for slow walking, is higher than our static weight. Then we will roll on our foot, and then we will push with the toes to take the next step. And again, you will see this dynamic effect, which will give you a dynamic force amplitude which is higher than the static weight. So heel strike, toe off, rolling on your foot in between. This is the way in which the force varies under our feet when we are walking. Of course, if we are walking slow, these effects are not so pronounced. If we are walking fast, then these two effects, the heel strike and the toe off, will be much more severe. So you could get to dynamic amplification factors of about 20–25%. Of course, what I forgot to tell you is what is the definition of walking. The definition of walking is as it is in the Olympics. One foot should be constantly in contact with the ground. So we don't have both feet in the air at the same time. One of our feet is constantly in contact with the ground. This is how the force will vary. Now, what can happen here when we walk? What can happen is that we have a certain pacing frequency. So we will move our feet with a certain frequency. That means a number of steps per second. If this frequency will be equal to the bridge frequency, say in the fundamental mode, then what we get is resonance, and what we get is the maximum effect of our walking over the bridge. So pacing frequency equal to bridge frequency leads to resonance and to high amplitudes in the bridge motion. So, what is the walking frequency? Well, the pacing frequency. Well, we have results on that. We have very good empirical results concerning the pacing frequency. The best known of these results are due to a Japanese researcher called Matsumoto, which measured on a total of 500 persons their pacing frequency. And what he obtained was that the pacing frequency has a Gaussian distribution with a mean value which is at around 2 steps per second. So essentially, we move at 2 steps per second. Most of us move at 2 steps per second. Very few of us walk at less than 1.3, 1.4